Welcome to part three of the three-part series on vector math. This is the last part, and this is probably, I think this is probably the most, stereotypically the most difficult method, just because, in grade school, you're taught a lot about geometry and trigonometry and everything. But for a lot of people, this is kind of their first look at algebraic vector math. And that's why it's a little hard to wrap your head around to begin with. But just know that it takes elements of both the tip-to-tail method and the parallelogram method, and then it also kind of does some other wonky stuff to it. Okay? You're gonna have to just follow along. It's once you've accepted that it works, it's pretty straightforward, but it's kind of abstract. So instead of seeing these as parts of a shape, see these as lines of motion. So like if, for example, you're going down the road, because you start and end at a point, or because you start at a point and you're going some speed, that you are making a vector by you driving. Okay. This all kind of relates to that. And in more later, topics in physics and, most at least engineering-based STEM and all of that, less so biology, I would imagine, you are going to use vector math. And this is the way you're going to use it from, basically from physics 1 onward. So we are going to, instead of redrawing these two to like line up with each other and finding the resultant vector like that, we're going to find each individual x and y component. And I kind of touched on that in I think part 1, but I'm going to redo it anyway. So if we look at the vector 1 here, and I'm going to draw a like this. This is the x, and think of this as a graph, okay? So this is a graph where your line starts at 0, 0, and it goes in the negative direction at 100 miles an hour into the 4th quadrant at some angle. Okay? There is a portion of that line that happens in the x direction, and there's a portion of that line that happens in the y direction. Okay? And since I drew this to scale, and this is kind of how you will always have it, either you will be given an angle, so either you'd be given what this angle was already, or you could find it by doing this method. Those two we know create a right triangle. Why did you highlight? Okay. So we can figure out what those two components are by using law of sines. So we're going to do, let's see, sine of 90 over 100 equals, oh, I guess we can't do that quite yet. We have to use the fact that I've drawn it to scale. So this, the vertical side of this triangle is 4 blocks, for whatever units, 4 units long. Okay, and this one up here is 3 units long. And because this is a right triangle, we can figure out how long the hypotenuse goes by doing h equals the square root of 3 squared plus 4 squared. And that equals 5 units, okay? So if we know that The blue line spans 5 units. And we know that the x and y components span 3 and 4 units respectively, then we could figure out how many units are in that, or how many miles per hour are in that. So I'm going to use this methodology. So if we say there's 100 miles an hour, mph per 5 units, and we know that there are 4 units vertically, we can use a ratio to figure out how many miles per hour that is. So that's 100 times 4 divided by 5, so we get 80. 80 miles per hour. And that is the y component of this line. And that y component, because these are vectors, oh goodness, we've been launched. Okay. Since these components are vectors, they have their own directions as well. It's almost like if you think about the tip-to-tail method where we added 2 vectors together to find the resultant vector, that's kind of what this is like, but our resultant vector is the one we start with. Okay. Now this is one way to figure out what the vertical component is. And we could do this again for the horizontal, but I'm going to use a slightly different method that is more in line with what you will be doing, down the road in future classes and generally in life. And that is, we're going to find what theta is. So if we use SOHCAHTOA, we have one side, and we have the hypotenuse, and the side that we have is opposite. So we have to use the SO version, or the SO component of SOHCAHTOA. So we get the sine of our angle equals opposite over hypotenuse. So if we do the sine inverse of 80 over 100, we get 53.13. And if you guys are, following along with all of the parts, you might think that that angle is a little familiar. And that just means we're doing our math right. So our angle is 53.13 degrees. So if we go back, let me rewrite that. SOHCAHTOA. Okay. If we go back to SOHCAHTOA, we are looking for the x component, because this is the y component. Okay. We are looking for the x component. So that's a variable that is adjacent to our known angle. And we can so since we're dealing with something adjacent to the known angle, we have cosine, or no, that's the opposite, or tangent. So I'm just going to erase the SO part of our SOHCAHTOA. Now, this is kind of a crossroads or a fork in the road. You can decide which one you want to use. I would recommend using cosine because we were given the hypotenuse when we started the problem, so we know there is a rounding error if we use that. If we used 80 miles an hour, because it's a whole number, there's not going to be rounding error in this particular case, but usually it is not as cut and dry as these whole numbers are. Usually there's like infinite decimals and all of that. And later down the road, when you get into forces and stuff, signing the SO and the K part of the SOHCAHTOA, so the sine and the cosine of everything, comes in handy. You hardly ever use tangent. So I would get in the habit of using cosine and sine for this. So if we do the cosine of our angle, so 53.13 equals the adjacent over the hypotenuse, we get x equals 100 cosine of 53.13. And that is 100 times the cosine of this is 60, just straight 60, so 60 miles per hour. Sweet. So if I'm going to make a little, I guess we'll use this. So V1, the x component is 60 mph, and the y component is 80 mph. And earlier I was saying that these guys kind of, the components have their own directions as well. The x component is going in the positive x direction, and the y component is going in the negative y direction. So over here in our bookkeeping, I'm going to make this a negative number. Now we're going to do this again with vector 2. Get my colors here. So V2. We get x and y. So the x component of vector 2 is 0 because our vector is strictly in the y direction. So it's almost like a portion, when your angle or when your vector is at an angle, there's parts of it that exist in one direction. Our vector right now is already in one direction. So the components reflect that. Okay. Now, this is what we have so far. And this is where the algebraic term comes from. I guess the algebra comes from like up here. This is kind of algebra in a sense. But from now on, all we do is just summations. So the x component of the resultant vector equals the sum of the x components of all of the other vectors. So since we have two vectors, that becomes 60 plus 0. So it's all of the x components of each vector that you're adding together. You add all of those together to get the x component of your resultant vector. Okay, which equals 60 mph. Our y is the same thing. So we have, in this case, we have a negative 80 plus a 120, and that is 40, positive 40 miles per hour. Okay. Now, this is great and all. So if I were to draw these, we would have, if I make one of these boxes 10 miles an hour, even though earlier we found them to be 20, I'm just going to blow it up a little bit for just this little segment. This is 60, okay? And then this one is a positive 40. And our resultant vector is the hypotenuse between those two. Going like this, okay? So we still need to find what r is, and we still need to find what theta is. But since we made this triangle using the x and y components, we know that it is a right triangle, which means we can find what r equals by using Pythagorean theorem. Okay, and if I plug that into my calculator, we get r equals 72.11 miles per hour. And we can find what that theta is by using law of sines. We could use law of cosines. Just whatever, we could use either one of those. I think in both parts 1 and 2, I use law of sines, just because that one's a bit easier. But you know, I'll use law of cosines this time. So we get r equals the square root of a squared plus b squared minus 2ac aab cosine C, or cosine theta in this case, because I've altered it slightly to match our variables that we're using. So we have, this is 72.11 equals the square root of 60 squared plus 40 squared minus 2 times 60 times 40 times cosine of theta. Wow. And now we get to do some pretty intense algebra. So we square both sides. And I will do this. So this becomes 5200 equals 60 squared plus, this should be squared, 40 squared minus 2 times 60 times 40 times cosine of theta. Okay, so I'm going to subtract these from both sides, these two right here. And I get, so minus 60 squared minus 40 squared. Bonkers. I just got, oh, I see what I'm doing. Okay, so I just got a 0 here, and this is a learning opportunity. So we can't use this method if it's a right triangle. That's good to know. It's been so long since I've been taught how to use law of cosines that I just, okay, where did that come from? That I just kind of forgot about that little tidbit. That's fine, we'll use law of sines. It goes way faster anyway. So sine of 90 divided by 72.11 equals the sine of theta divided by 40. Because 40 is opposite of sine of theta. So that becomes 40 sine of 90 divided by 72.11, and all of this is sine inversed to equal theta, which should equal the same number it's been equaling since part 1. Yep, 33.69. Okay. And that's theta. So this one took less time than the triangular method. It took about the same amount of time as the parallelogram method, but it is significantly easier in my opinion. Because you don't have to worry about all of those internal angles and all of those unknowns and everything. You just look at each individual vector and you find the components of each individual vector and you add them all together. This method, you can, it doesn't matter how many vectors you have, you can use this method. If we had vectors 1 through 10, we could use the tip-to-tail method, but that would, oh goodness, I dropped my thing. That would look like, so you have this, then you have maybe that, and 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 maybe that. And your resultant vector would be from there to there. Okay? That looks like a nightmare. And we could do that super easily by using the algebraic method. Because each one of those vectors has an x and a y component, and the resultant vector sums up, or the x and y components of it sum up to equal the x and y components of the resultant vector. Now, I never touched on how to subtract vectors. You will always just flip the direction. It will go the opposite direction of the way it's going when you add it. So for vector 2 here, if I were to subtract it, the vector would be, let me erase this end, the vector would be doing this. And you would do your math accordingly. And if we were to subtract vector 1 here, the vector would be going this way, and we would do our math accordingly. Now, that would just change some signs in our components here. It's quite a bit more difficult to do that using triangular or parallelogram. just because you then have to draw your shapes wrong. Weird, you have to draw them differently. And same with multiplication. So you're not in physics 1. You're not going to be asked to multiply two vectors together, but you may be asked to add like vector 1 plus 2 times vector 2. And whenever you're doing that with the other methods, it can be really difficult because you have to basically double the length of your vector. But in this method, you don't have to do that. Your x and y components will just become double. So 2v, so if we did 2 times v2, we would get the x component to be 0 and the y component to be 240. That's it. That's all we do. And then we would just sum them up accordingly with that value instead of the 120. So I would highly recommend, if you only want to learn one method, I would highly recommend this method. And I do believe that concludes the 3-part series on vector math. I hope it helped you a little bit, and you know, I hope it helped you more than a little bit, actually. If you have any suggestions for future content and stuff, feel free to leave a comment. And you know, if you need more help in the future, you know where to find me.